Okay.
Hello everyone. It is my pleasure to introduce our next speaker, Chengxi Wu. The title of his talk is Self-Similarity in the Thurston's Teapots.
Okay. Hi. So firstly, thank you so much for giving me a chance to speak. So the topic that I'm going to talk about is actually somewhat related to one of my previous projects. So I did some previous works with these collaborators, Harry Bray, Diana Davis, Catherine Lindsay, and Giulio Tioso on the object that I'm going to talk about. And actually, in one of the papers with Catherine Lindsay, that has already been published in Ergodic Theory and Dynamical System in 2025, we have a comment which says that, well, a consequence of our algorithm is that we will have some particular properties of the shape that we care about. And actually, when we had that observation, we asked around a little bit. For example, we asked Sarah Koch and a few other people. They all said that it's kind of obvious and it follows obviously from Slomiak's one of his previous arguments. But then later I thought, well, but on the other hand, there are also some other people who told me that maybe it's not that obvious. So I decided to write it down, and then yeah, it's a really short note, and it has already been. It's going to appear in contemporary mathematics. So basically the content of today's talk is going to be in this archive paper. Yeah, so it's just a short note on an interesting fact related to an object that we thought about before. And yeah, the reason that I chose this is because it's related to fractal geometry and also to dynamics. So what exactly is the object, like the Thurston's teapot in the title? Well, this is a mathematical, like a geometrical object that was described in William Thurston's, one of his last papers, Entropy in Dimension 1. So basically it's a way to encode the topological entropies of certain unimodal maps, in particular real quadratic maps. So if we consider the set of all the real quadratic maps such that the critical point eventually goes back to itself, because the critical point has finite forward orbit, it has a finite Markov decomposition of the interval. So it has like a topological entropy, which is the log of some algebraic integer. In particular, it's the log of some Perron number. Well, once we have a log of some weak Perron number, once we have the an algebraic integer, we can consider our conjugates if we consider like the field extension over Q. So we can just plot all the Galois conjugates of that particular E of the topological entropy, exponent of the topological entropy. And that would be a two-dimensional object, and you can see the picture of that. That object has been described in previous works by Giulio Tioso, but in Thurston's last paper, he also mentioned that we can build a three-dimensional object instead of the two-dimensional thing. So we can consider a subset of C times R. So where R is like the exp of the exponent of the topological entropy, and then the C part is just like all the Galois conjugates. So it consists of like countably many numbers, Z lambda, such that lambda is the topological entropy of some unimodal map. So a map with a single critical point, such that the critical point eventually goes back to itself. And then Z is one of the Galois conjugates of lambda. And after we have these countably many sets, we do a closure. So that's a closed subset of C times R. And why do we care about these kind of sets? Well, they gave us a necessary criteria on whether or not algebraic integer can be the exponent of the topological entropy of some unimodal map. So in that paper, Entropy in Dimension 1, the main conclusion is that any weak Perron number can be the exponent of the topological entropy of some interval map, some continuous interval map. But potentially the interval map could have like complicated topology. It may have multiple critical points. So if we restrict ourselves to the case where there's only a single critical point, that will be like, it's not true that any weak Perron number is going to be the exponent of the topological entropy. And one way to describe that, one way to give a condition on that is to require that, like, well, if we look at all its Galois conjugate, it has to lie in this T. So that's a necessary but like not, yeah, that's a necessary but not sufficient condition. Or at least we don't think it's going to be sufficient. Yeah, but at least it's something that we can check. Well, also, well, just by that condition alone, of course, that's not really a computable condition. But like in one of my two of my previous papers with the collaborators, we actually found the algorithm to actually turn this, like all the Galois conjugates lying in T into a condition, actual computable condition. So we can algorithmically verify whether or not a point in C times R. Well, if a point is not in T, then we have an algorithm which is going to terminate a finite amount of time. So that's, yeah, that's basically a necessary condition. The necessary condition is that if you run the algorithm, it's never going to terminate. Yeah, in other words, it's a way to say that, well, some algebraic number cannot be such an entropy. And we were able to generalize the algorithm to some other complex quadratic maps. Basically, the complex quadratic maps that are lying on principal vanes of the Mandelbrot set in another paper with Catherine Lindsay and Julia Tioso. So these are some of the previous results. But like if you look at the picture of this particular shape, oh, firstly, why do we call it a teapot? Because we know that like the number itself is also going to be its Galois conjugate. So if you draw the picture, there's always going to be a line z equals lambda. So it's like a cylindrical thing and then together with a line. So it's like the teapot. But like if we look at the actual part, like the part of the teapot other than this line, then we can see some interesting features. So we see that like if we look at each horizontal slice here, different colors denotes different horizontal slices. So there's some kind of tree-like, almost fractal-like structures on each horizontal slices. And then also another feature is that if we look at the interior of the teapot, basically the part inside this unicylinder, we see that there are like these vertical lines. So basically, yeah, we can imagine that if we have some point inside the teapot, then all the points above it are going to be inside the teapot as well. Actually, this is also an immediate consequence following from our algorithm with Barry Davis and C. And yeah, for the outside, and also it looks like outside behavior is going to be quite different from the inside behavior, and that's actually also the case. So we have basically different theories for outside, inside, and for today we are mostly going to focus on the inside. Okay, so from the algorithm, we immediate consequences that we explain these vertical lines. So yeah, Catherine Lindsay call it the icicles. So basically, if we have some point, then the whole vertical line is going to be inside that. But there's another observation, which is that if you look at the places with the same color, then there's a lot of like tree-like structure. So there's some kind of self-similarity. And if, yeah, so this is an example. If we consider any lambda from 1 to 2, then we can consider this horizontal slice. And this is actually, I think this is not a good slice. This is the slice lambda equals 2. But yeah, so if we look at some other slices, for example, lambda equals golden ratio, there will be some even more interesting feature. But even at this particular slice, we can already see something interesting. So if we look at these trees, yeah, there's some kind of fractal-like self-similarity structure. So, and also another other thing is that if you look at like the loop phenomena around different points, we are going to see different kinds of self-similarity structure. So the idea of understanding this, actually for this particular slice, uh, there are few, like Slomiak has few papers that have already done some of the analysis of these slices, but like our argument can work on all the horizontal slices, not just these lambda equals 2 ones. Okay, so the point is that, well, we already understand like what happens for those vertical structures. Let's try to see why we have this kind of fractal-like structure at each horizontal slice. So, okay, here by horizontal slice, we consider like a horizontal slice of the t, but we only consider all the z's where the epsilon value is strictly less than 1. So we forget about outside of the unit circle. Okay, the theorem one is that if we along a slope which correspond to cut it along a height which correspond to the exponent of the topological entropy of a post-critically finite unimodal map. Here, post-critically finite means finite a critical point has finite has finite uh, forward orbit. So in particular, the topological entropy is going to be log of an algebraic integer, and this lambda is going to be algebraic integer. So if we do that, then actually we can describe this slice as what's called the Mandelbrot set of a graph-directed iterative function system with a parameter z. So here, by a graph-directed iterative, I think earlier we already in some previous talks we have already seen graph-directed iterative function systems. But here, like each function is no longer just fixed, so each function has a parameter, and the parameter is parameterized by some complex number z, and z is like basically the number with absolute value less than 1. And essentially, z is like the expansion factor of this graph-directed iterative function system, so we require this to be a contracting. And here, by saying the Mandelbrot set, we just mean we consider all the parameters such that the limit set contains a particular point. So here, the particular point is 1. The motivation is that let's recall in the quadratic dynamics of in the dynamics of quadratic complex polynomials, we see that the Mandelbrot set are exactly all the points where the critical point 0 does not go to infinity on the iteration. So here we also, yeah, this is like analogous to that. And yeah, so this is theorem one. Basically, we can interpret these horizontal slices as related to certain families of graph-directed iterative function systems. And maybe I can say a few words. So the details of the proof is in the notes that I mentioned earlier. But like I can say a few words about the idea of how we construct this graph-directed iterative function system. So once we have a post-critically finite unimodal map F, we can just look at the forward orbit of the critical point. The forward orbit of the critical point is going to decompose the interval into finitely many subintervals, and that's going to form a Markov decomposition. So basically, the graph is literally just that Markov transition graph. So each vertex corresponding to one subinterval, and then the forward image of one interval covers another interval, if only if there's an edge between them. And here, when we consider the limit sets, we are considering all the infinite sequences that end up at the last subinterval. And then for each subinterval, we have the function, where if it's less than the critical point, we have one function. If it's to the right of the critical point, we have another function. And for each infinite sequence that ends at the last interval, we can just compose all the corresponding functions corresponding to like the itineraries of each of the subintervals. And now we basically start at 0 because all these functions are just contractions. So we can just start at like assume that the input is something bounded. For example, yeah, essentially just make it 0. And then now given any parameter z, this whole process is going to give us basically essentially the idea of what happens after we travel through this whole thing, and that will give us a point in the limit set of this graph-directed iterative function system. And here, the fact that z is going to be a Galois conjugate of the entropy. Well, if z is literally the entropy, then if we consider the backward itinerary of 1, that's going to be just a point in the limit set of this of this uh, graph directed GDIFS, And that point is going to be just one because eventually it hits like one. If we consider any of its Galois conjugates, of course, because all these are like algebraic equations, we are still going to get one. So basically, that's the intuition. Why we once when we pick any of the Galois conjugates, it's still going to hit one. Of course, the actual proof is more complicated. It involves some like really messy combinatorial argument, which is like quite long. But intuitively, that's kind of the idea. Yeah. So, in other words, what I meant to say is that it's possible to very explicitly write down these graph-theoretic iterative function systems, and the number of vertices are literally just the size of the Markov decomposition of this PCF in postcredibly finite unimodal map F. So once we have this, we can make use of the argument in Tanley's paper on the correspondence on the similarity between Mandelbrot sets and Julia set to essentially show that we can find many points in these horizontal slices where there's local self-similarity around those points. And also, locally, those points just look like the limit set of the corresponding graph theoretic iterative function system with z being those parameters. So the idea is that if we read Tanley's proof for the similarity between Mandelbrot sets and Julia sets, the key idea, like one of the key technical results is that, like she said, that there are four conditions. If we can verify these four conditions, then we have this kind of correspondence between the Mandelbrot set and the Julia set. Here that we can think about the Julia set as the limit set of this GDIFS, and then the Mandelbrot set as like all the Z, so that the field Julia set contains one. So that's the intuition. Okay, so the idea is that let's construct a space which is a bundle over the parameter space. So for each parameter, we just put like we have the corresponding limit set, and then we just put them together. So that will be a subset of C times C. So where the first C is the parameter, the second C is where the limit set lies on. So firstly, we need to show that that set is closed, which is obviously true, basically just by construction. And then the second condition is that we need to have a dense set of continuous sections, which is also true because we can just consider all the periodic paths in that graph that correspond to the GDIFS. So those are the countable dense set of continuous sections. And next, we need self-similarity of the fibers around zero. Well, that's because yeah, these are graph theoretic IFS, and we can, for a lot of those points, we can basically literally just say that, oh, well, there's going to be self-similarity. Yeah, because the limit set themselves are basically fractals. And like the limit set themselves has self-similarity. We can just look at the corresponding paths and then do concatenations. Yeah, that's how we get self-similarity. And then the last one is that uh, here we require that okay, so we require them to be self-similar respect around certain around zero. So that means that we have to do adjustments of those limit sets. We have to move the limit sets up and down a little bit so that the original point like one becomes some other point, and then sorry, yeah, so that the original point becomes some other point, and then we pick the self-similarity around zero. The way that we do that is that, well, suppose we already have some point Z where we want to show we will want to show the conclusion of theorem two, then that point correspond to an infinite path that ends at the last subinterval. So yeah, there's an infinite path along the graph. So we just look at for each other neighboring limit set, we just look at the corresponding point in the limit set. So that's going to be basically it's going to be smoothly dependent on the parameter on this z parameter, and there's going to be self similarity at every point. Yeah, so we can just basically rewrite condition 3 and 4 by checking those two conditions. So yeah, we have that we can write down those particular fixed points at the limit set, and they vary smoothly, and also there's self similarity around them. So by checking all these conditions, just following Tanley's work, we get what we want. And lastly, in terms of further questions, uh, well, this result basically gives us a way to show that we have, gives us very good geometrical descriptions on the local geometry of that particular set. But well, then there's I think there's a question that Julio Teoso raised a while ago, which is that if we just literally look at the boundary of this set, well, what exactly would be its cost of dimension? So in order to understand that, one potential way of doing it is to first see whether or not we can find a lot of points so that our theorem 2 works. And then if that's the case, for each point, we can study the geometry of the limit set. And then the limit set of that graph-directed IFS and try to understand the Hausdorff dimension of its boundary. And potentially taking the supremum of all those Hausdorff dimensions is going to give us the Hausdorff dimension of the boundary of these slices. So yeah, whether or not we can accomplish that by going through this whole approach, I think is one of the further questions. And also, I'm currently working with a couple other collaborators on trying to extend this to other fields. So instead of considering C, we can consider, for example, the p-adic fields or the fields of pursuit series over uh, fields of power formal power series of a C, and then and then do the quotient field of that. So basically, the fields of formal Laurent series over C. So we can consider certain other kinds of fields and try to carry out the whole computation. We also have some algorithm there, but like we are still working on implementing them and understanding the picture. Yeah, so I think that's all I have prepared.
Thanks, the speaker.
So any question? Yeah, so
Any
the details, I think it's in the notes.
any more question to the speaker? If not, let us thank the speaker again. Our next talk will start in 7 minutes.